Okay, let us begin. So welcome all. Welcome to this workshop on McDonald polynomials. So today we are going to have our first lecture by Radhika Ganapathy from IAC, and she will talk about affine and extended affine Weyl groups. Radhika.
Okay, thank you. Thank you, Venkatesh, for organizing this workshop and for the invitation to speak here. So I'll be giving 3 lectures basically to cover the material about double affine braid groups, double affine Weyl groups, and also touch upon the construction of the double affine Hecke algebra. So today I will sort of do the preliminaries needed to construct the affine braid group, and in the next lecture I'll construct the affine and the double affine braid group. So for at least the first 1 or 2 lectures, let me write down the references I have used. The first one is this book by MacDonald. It's Affine Hecke Algebras. And orthogonal polynomial by MacDonald. There are also these lectures by Krylov, so lectures on affine Hecke algebras and MacDonald conjectures by Krylov. This is available on archive. And again, another article which I found helpful on archive is the Cherednik algebras, MacDonald polynomials, and their combinatorics. This is by Mark Heyman. And then, of course, Lie groups and Lie algebras by Bourbaki. Sorry. Yeah. Okay, and I will update this list of references when I get to the construction of the double affine Weyl group and the double affine Artin group, particularly for the case GLN. I'll update this list when I get there. Okay, so today I want to, as I said, basically the material I'm going to cover today is essentially contained in the discussion today. Is an overview of the first 2 chapters of MacDonald. Of first 2 chapters of MacDonald. So I will talk about affine root systems. I'll begin with some very basics about Coxeter groups, braid groups, and Hecke algebras that come from that one can obtain by looking at the group algebra of a Coxeter group, of a braid group. And then I will talk about affine root systems, alcoves, and so on, and discuss the both the affine and the extended affine Weyl groups in some generality, not in the generality that MacDonald has done, but not in a very specific example also. So I will do it in some generality, and towards the end I will explain what each of, I'll just list what each of these objects that we introduced today are, what they look like for type A. Okay, I think type A will be sort of the focus, at least my understanding is maybe it will be the focus in the lectures to come. So I'll explain what they look like for type A. Okay, so Coxeter groups. Just, I'll be brief about the first few sections. Maybe a standard reference for this is the Book of Humphreys. Okay, so let I be a finite set. M from I cross I to z greater than or equal to 1 union infinity be a function satisfying m of ij equals m of ji greater than or equal to 2 for all I not equal to j in I, and m of I equals 1 for all I in I, and let W be the group. I mean, it has the following presentation subject to the, it has generators SI indexed by I and I, subject to the relations SI Sj to the power m of ij equals 1 whenever m of ij is less than infinity. Okay, and the groups appearing this way are called Coxeter groups, and this Wi is called a Coxeter system. And so note that the generators SI satisfy SI square is 1. So the defining relations can be replaced with the braid relations SI, SJ, SI, and so on equals SJ, SI, SJ, and so on for all I not equal to J in I, whenever M of Ij is less than infinity, and the quadratic relations. So these are called the braid relations, and then we have the quadratic relations. SI square is 1 for all I and I. Okay, so this way of writing down the relations in the Coxeter group will be helpful when we write down the braid group, the associated braid group, and the associated Hecke algebra. And maybe I'll quickly go through this as well. Any W in W is a product S1 say through SQ of these generators, which we call simple reflections. And let L of W be the length of W. So this is the minimal length of such an expression for W. So the minimal length of such an expression for W. And and such an expression is called a reduced expression. Of course, given any W in W, there might be many different reduced expressions for it. So a typical element may admit many distinct reduced expressions, but one may get from one to the other using the other braid relations, but one may get from one to the other using using these braid relations. So you can refer to, maybe a reference for this is Bourbaki, chapter 1, I guess. Yeah. Okay, and given any Coxeter group, one can talk about the associated braid group of the Coxeter group. So let me also discuss the construction of the braid group. Let Wi be a Coxeter system. The braid group BW associated to Wi is the group generated by the set Ti, I and I, subject to the braid relations alone, subject to the braid relations. Ti, Tj, so on. Ti, so on is Tj, Ti, Tj, and so on, where you have M of ij factors on each side. And so this is for I not equal to j in I. Yeah, so basically the braid group has a description identical to what we had for the Coxeter group, except that we ignore we omit the relation that SI square is 1 when when we talk about the braid group. Okay, and so yeah, basically is similar to Coxeter groups, but quadratic relations are omitted. Okay, and again, for any W in W, for so for any W in W and a reduced expression W as SI1 through say SI W. Again, it follows that the product Ti1 through Tiw does not depend on the choice of the reduced expression, because we have already the braid relations will take care of that. It will allow you to go from one reduced expression to the other, and the braid relations still hold in the braid group, so it doesn't depend on the choice of the reduced expression. And so let us denote this product as say TW, or I don't know if TW. Then the set TW W in W generates BW, the braid group BW, and we have the relation TW times TW prime is TWW prime if the length of W prime equals the length of W plus the length of W prime. In this holds in BW, and yeah, and this gives another presentation for and
if the length is less.
The length is less. This won't hold true.
Okay.
Because I have not killed ti square, right?
Right.
Yeah. So if the length is less, this is yeah.
I have a question.
Okay.
Say TW generates PW, but doesn't TI itself generate PW?
Yeah, it does. It does. The
So
TIs
then
are the
obviously TW generates.
yeah,
PW.
yeah. So yeah.
Are
In
you
fact,
trying to say something more?
No, I was trying to write down a presentation with the TW as generators and the relation as this.
Thanks.
That's all I was trying to do.
Okay.
Yeah. So this is an alternate presentation to what we had earlier. That's all I was trying to do.
Okay.
Yeah. Okay. And
But
we have
sorry, you're not saying that every element of BW is T of the form TW, right? I mean, that's, yeah. But it just generates.
Yeah.
Yeah.
I have not killed these relations here. So yeah. Okay.
So
So we have a sorry.
Hello, is this TW, whatever you have relation defined, is this defining relation for BW? Can you say that?
Sorry.
This TW dash equal to TW dash, if
Yes.
length is additive,
Uh-huh.
so is this relation is the defining relation for BW?
Yeah, it is a defining relation. It is, we have this relation and
Okay.
this gives another presentation for BW.
Okay, thank you.
Or you could, instead of using TW and TW prime, I could use a TSI and a TW prime and then say that if the length is more, T of SW is greater than the length of W, then this relation still holds and so on. Yeah.
Okay.
Okay, so we have a surjection. We have a surjection from BW to W, sending TI to SI, and the kernel is generated by TI squared. Okay, and so this is just a sort of brief discussion about braid groups, and associated to any braid group, we can talk about the, given any braid group which comes from a Coxeter system like this, we can talk about the associated Hecke algebra. Again, this is a fairly general construction. Sorry, Hecke, I wanted to say Hecke algebras. Okay, Hecke algebras. So let Wi be a Coxeter system, and let tau from say I to C cross be a function such that tau of I equals tau of j whenever Si and Sj are conjugate in W. And write, I'll write this as tau I, which is easy, which is basically tau Si, which is tau of I. Okay. The Hecke algebra the Hecke algebra H tau of Wi. It depends on this one parameter family that we have picked, Hi of Wi attached to this Coxeter system. Attached to the Coxeter system. Wi and the parameter tau is the C algebra with generators Ti, I, and relations consisting of the braid relations that we just discussed, consisting of braid relations and additionally these Hecke relations or quadratic relations. Whatever name one chooses. So this is Ti minus tau I times Ti plus tau I inverse is 0 for all I and I. Okay, and so the Hecke algebra is the quotient of the C algebra of the braid group, and the relations you have here are the braid relations and these Hecke relations. So in particular, this relation implies that Ti is invertible. I mean, you can just sort of write this out and you'll see that Ti is invertible, and we have Ti minus Ti inverse is tau I minus tau I inverse. And you have and now consider the natural surjection. CBW, this is the group algebra of the braid group to H tau of, what is the notation? H tau of W. Maybe I'll just write H tau of W instead of H tau of Wi, sending Ti to, Ti again. This is surjective. And the kernel is generated by the Hecke relations. Yeah, so basically H tau of W is BW mod Ti minus tau I times Ti plus tau I inverse I. Okay, so associated to a Coxeter system, we talked about what the braid group is, where we basically ignore the quadratic relations, and then from the braid group we can and given a parameter tau, we can talk about the Hecke algebra that comes from it, which can be thought of as a quotient of the braid group by quadratic relations. Okay, so this is sort of everything here. Everything we have done here so far is general, is quite general. So we will talk about. So we want to construct the corresponding to the affine and the extended affine Weyl group. We will construct the corresponding braid groups, which will be the affine braid groups and the affine braid group and the extended affine braid group.
Before that, sorry, I have a question. So I'm used to these Hecke algebra where the parameter is q, and it's Ti squared is qti plus qt1 plus q minus 1 Ti.
Yeah.
So now this looks a little different.
I think you can just scale it by choosing. Sorry, you can just scale. Yeah, I think you mean T minus 1 times T plus Q or something.
That's right.
Yeah. Right. Yeah. So you can scale the generators by choosing a square root of Q and get this from.
So I should put tau I equals square root of Q for all I. And then I should just scale each Ti by maybe.
Something like So I'm also more familiar with this. But anyway, so this is there is just a rescaling involved after choosing a square root of Q.
Okay.
Right. So this natural surjection from CBW to the Hecke algebra, is this Ti going to tau I? Or?
No, Ti going to Ti. The Hecke algebra, tau i's are just complex numbers. You see, tau I is a function from I to C cross.
Okay.
tau of I is tau I, and tau i's are just complex numbers. So the relation, okay, maybe this is, I don't know if this is standard notation, if the people use different notation for this and this, but anyway, so Ti goes to Ti. In H tau of W, there is this additional relation, which is this Hecke relation. So this quotient, so this natural surjection will have exactly this as the kernel. Okay. 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 And yeah, so so I guess I'll say this maybe. I hope this is standard, but this is what I saw in the references. Okay. TW, W and W is used to denote both the elements in elements of the braid group and their images in the images in H tau of W. And yeah, so there is a theorem which I will probably not prove. I mean, I could give a sketch, but I've already spent. Okay, so the set TW, W and W forms a C basis of H tau of W. I can give, so one reference for this is Humphreys. You can find this in Humphreys. You can also find this in McDonald's book. McDonald's book, chapter 4, I guess. Chapter 4 specifically discussed in the context of affine Hecke algebras. But I'll skip this proof. Okay. So this was sort of a quick overview of Hecke algebras associated to braid groups. So when we define our affine Weyl group, and from there we construct our affine braid group, the affine Hecke algebra will be obtained from the affine braid group exactly by what we did now, by this construction that we just did. Okay, so I just wanted to do this in this generality. Okay, so now I want to start talking about affine Hecke algebras. I will not get to the construction of the affine Hecke algebra itself today, I guess, but I will talk about affine and extended affine Weyl groups today, and also talk about this more general notion of an Iwahori Weyl group. But anyway, so yeah, affine root systems. Okay, the reference for this is chapter 1 of McDonald. Or you can also look at Bourbaki. But okay, so I'm not going to do the construction in the generality that McDonald has done it, but still to some extent. And it'll sort of be an overview, so there will not be many proofs. And also I will, towards the end, explain what everything looks like for the type for type A. Okay, so these are similar to finite root systems. These are similar to finite root systems.
Can I ask a question?
Yeah, sure.
What value of tau I should I choose if I want to get the group algebra of the Coxeter group?
Tau should be 1 for all. Yeah, tau should be 1, right? Tau should be identically 1.
Identically 1. Okay.
Because then I will get Ti square is 1. Is that answering the question?
Yes, but I was not getting Ti square equal to 1. That was my problem.
So if so, okay, so maybe I should have said this. I have it in my notes. I thought I'll skip it because I'm pressed for time. Okay, so you see, if I take tau to be tau from I to C cross to be tau is tau of I equals 1 for all I, then okay, so what should I do? Okay, so maybe just let me just write this here and then I'll erase this. Then H tau of W is this braid group CB of W mod Ti minus 1 times Ti plus 1. Right?
Okay. So okay, I got this. Okay,
This
that's
formula
the tau
is,
one. Okay, got it. I read your T's and taus incorrectly. Sorry, thank you. That
sorry,
answers.
sorry, maybe my note. Yeah, okay.
Fine, thank you.
Yeah. Okay, so yeah, exactly. So I guess when tau is identically 1, the Hecke algebra that you get with respect to that parameter tau is the group algebra of the Coxeter group. Okay, so sorry, so I'll just erase this. Okay, and there are I just want to highlight a few points about affine root systems, both drawing their similarities and differences with the finite root systems that I will assume for these lectures. So there are infinitely many affine roots. And so this has an axiomatic definition and a classification and a classification in terms of using diagrams, but not so when one is talking about finite root systems, we have the usual Dynkin diagrams. Here one has the affine Dynkin diagrams. Using these are affine Dynkin diagrams. And so we have, and then when this leads to the definition of the affine Weyl group and length functions. And of course, we have the notion of fundamental domain, just like the Weyl chamber. You have a notion of a fundamental domain here, which is called an alcove. No, they're not called Weyl chambers here. They're called alcoves here. So for, as I said, one can look at McDonald's book for the very general construction, but today I will only consider affine root systems that can sort of be very easily obtained from finite root systems. So we will consider affine root systems that come easily. I mean, I have to make this precise, but I will do that in a minute from finite root systems. So basically, the affine root systems I'm going to consider are integer translates of finite root systems. So, okay, so maybe let me quickly go through this affine functions, affine reflections, and translations. Okay, so we will start. Let V be a Euclidean space with an inner product, and we will identify V with V star using this inner product. Okay, and okay, so yeah, so sorry. Yeah, okay, so let F be the set of affine linear functions on V. So I should point out here that the more appropriate way of doing this would be to start with an affine space. That is basically, it's a set on which this vector space will act, this vector space V will act faithfully and transitively. But once you make a choice of a base point, you can identify the affine space with V itself. And in some sense, I've already done that to avoid some I mean, it is not any more difficult to write this in that setup, but somehow I've so I have identified the affine space with the vector space itself after making a choice of a base point. And so I'm going to think of these functions as functions on V. Okay, so these are, that is, functions from V to R is a sum of linear and constant functions. Okay, so basically F is basically V plus R C, where C in F is the constant function 1. Okay, and so for any F in F, we can talk about dF, which is called the gradient of F, which is the projection basically onto the first factor, projection onto the first factor. Okay, and we may extend this inner product we have on V to F by setting the pairing between F and G to be equal to the pairing between DF and DG. DF and DG are now elements of V. Okay, and let F in F be non-constant. Then set F check to be 2F. I mean, this is very similar to what we have for finite roots. Okay, so F check is 2F over this pairing, and the set HF, I guess, is, which is denoted as, it's denoted as HF, which is F inverse of 0, is an affine hyperplane in V. And we can look at the reflection with respect to this hyperplane. SF from V to V is given by SF of X is X minus F check of X times DF, which is also equal to X minus F of X times DF check. Okay, and SF also acts on F. So SF of G is G composed with SF inverse, which is also, G composed with SF. Okay, and some more notation. So for V in V, we shall denote T of V from V to V as the translation by V. Translation by V. So T of V of X is X plus V. Okay, so
Sorry,
yeah,
can
so
I ask a question here?
Yeah.
So this SF, its square is 1. Oh, is it true that SF squared is 1?
yes, I have used it here already.
Ah, I see. And but if F was equal to C, for example,
Mhm.
then SF is in fact the identity map. Is it true?
If F was,
Bec-
sorry, give me a minute. I have to,
Because DF, I think if F is equal to C,
then
then
DF
if
is
I'm-
0. Yeah.
then DF is 0. Yeah, that's
Yes, exactly.
okay. So
Yeah,
I'm
exactly.
understanding correctly then.
Yeah,
So
yes, yes,
SF is
absolutely.
in that case, SF is very boring.
Yeah.
Okay, but it still squares to the identity. Okay.
Yes, yes,
Great.
yes.
Thank you. Thank you.
Yeah. Okay, so now okay, so let me talk about as I said, I'm not going to talk about affine root systems in the generality that McDonald has considered, but nevertheless I think it will include the examples that we are interested in, which is type A primarily. So affine root systems, so fix a finite irreducible reduced root system are contained in V, spanning V. So okay, and so I'll have some notation. Q is the root lattice, P is the weight lattice, Q check is the co-root lattice, and P check is the co-weight lattice. And I'm going to consider RA, which is the set of all alpha plus say NC. C is this constant function equal to 1. We'll sort of stick to that notation, and where alpha belongs to R and N is in Z. Okay. So we will be focusing our attention only on such root systems. Of course, one may always drop this assumption that the finite irreducible root system is reduced. Then I have to allow for some non-integers as well. But then going from this to any affine root system will require a bit more work, which I'm skipping basically. Okay, so these elements are called affine roots. So when we get to the example of GLN, I'll draw the picture for GL3 and or sorry, whatever, SL3 or one of them, and we'll see how these things look. These elements are called affine roots, and of course R is contained in RA, and W says the Weyl group of R, and WA is is generated by say SA A in RA, and this is the affine Weyl group. And clearly, W is contained in WA. So what we want to do is to obtain a nice description of the affine Weyl group. Okay, so but before that, remark. The translation by elements in the co-root lattice are they form a normal subgroup of the affine Weyl group, and in fact, WA is T of Q check. W is the finite Weyl group. Q check is the co-root lattice, and sorry, yeah, okay. Now, to see this, I'll just quickly explain the proof. Yeah, so let A, B, say alpha plus NC be an affine root, then you can check easily by these formulas that we wrote down that S alpha times SA of X is basically X plus N alpha check. So this is T of N alpha check of X. Okay, so because I've already, because the affine Weyl group contains such elements, I get all the translations inside all the translations with respect to the co-roots in the affine Weyl group. So yeah, so this tells me that T of Q check is contained in, is a subgroup of WA. And also you can, again, by the formula that I wrote up there, SA is basically T of N alpha check composed with SA. So WA is actually generated by W and T of Q check. And for lambda in Q check, we have W T of lambda, W inverse is T of W lambda, which implies that T of Q check is actually normal in WA. And so,
Sorry,
yeah, WA is basically it. SA is S alpha plus NC, this reflection with respect to this function.
Yeah, but
Sorry?
There might be a typo on both. If you look at SA and SA.
Ah, sorry. Thank you.
Yeah, thanks.
Yeah. So WA is this. Okay. Now, just like making a choice of simple roots in the finite Weyl group is equivalent to choosing a Weyl chamber. We have a similar setup here for affine root systems. So alcoves, that's what an alcove will do. Alcove, positive, and simple roots. Okay. Recall that a choice of simple roots delta for R, for the finite root system R, determines a Weyl chamber. C, which is the set of all X in V, such that alpha of X is greater than or equal to 0 for all alpha in delta. Sorry, I should probably say, yeah, the closure of the Weyl chamber is, and W is generated by reflections through the walls of C, right? And also R plus, the positive roots, is the set of all alpha in R, such that alpha of X is greater than or equal to 0 for all X in C, and R minus is minus R plus. These are all things that we know for the finite root systems. And we can do something similar for affine root systems. We can fix an alcove in V, and then that will allow us to talk about positive affine roots and negative affine roots. So for A in RA, let HA be A inverse of 0. The connected components of V minus the union of HA, A in RA, are called alcoves. Okay, and okay, so I want to now let CA be the unique alcove in C whose closure contains 0. So what is happening is you have these Weyl chambers when you look at finite root systems, but now we are also allowing integer translates of finite roots. So the Weyl chamber itself will get divided up into several alcoves. Each Weyl chamber will get divided into several alcoves, and there is a unique alcove that will contain the origin, which we sort of fixed when we did this identification of the affine space and the vector space. Okay, so we look at the unique alcove whose closure contains 0. Then basically CA closure is the set of all x in V such that AI of x is greater than or equal to 0 for 0 less than or equal to I less than or equal to n. So if the Weyl chamber has n bounding hyperplanes, then the alcove will have n plus 1 bounding hyperplanes.
I'm a bit confused. So why do you say there's a unique alcove whose closure contains 0? Isn't 0 on the boundary of an alcove?
No, alcoves are open for us. Yeah, it's in the boundary of an alcove. Yeah. So let me, shall I just draw
there be several alcoves whose closure?
No, I've already fixed the Weyl chamber.
In C.
I have unique alcove in C. I have fixed my Weyl chamber.
Okay. Sorry. Yeah, thanks.
Yeah. If I don't fix the Weyl chamber, yes, there are several alcoves that will contain the 0, but I fixed my Weyl chamber and I'm looking at the unique alcove in that Weyl chamber that contains 0. Yeah. And so basically, so as I said, if your Weyl chamber has n bounding walls, then the alcove will have n plus 1 bounding walls, right? With n plus 1 walls given by affine hyperplanes. And so maybe AI inverse of 0, 0 less than or equal to I less than or equal to n for some uniquely determined affine roots A0 through A0, A1 through AN. Here I guess the notation I'm using is A1 through AN are my finite simple roots. Finite simple roots which form the walls of the Weyl chamber that they determine. Finite simple roots. Sorry, finite simple roots. And these AIs are called affine simple roots. And of course, so by the notation so we have A0 does not belong to the finite root system. It does not belong to delta. It is some integer translate of some other of some finite root. That is it has non-zero constant term.
So Radhika, I guess it's a result, if you will, that every finite simple root is an affine simple root? Or
affine every so I have fixed my Weyl chamber. No, I mean in general, if I choose, so you see, I'll just draw the picture maybe for SL3. It is not true that any finite simple root. So what was the question? Sorry, let me make sure I process the question, bro.
Yeah, I was just asking. So basically, what you're saying is, given the definition of the chamber, the alcove CA, the walls include the simple root hyperplanes, and that is why every finite simple root occurs among the AIs.
Yeah, that is why the finite simple roots are. But in general, if I don't choose that alcove, I could choose some alcove away from the origin. Then it's only the gradients of those affine roots that will contain the finite simple roots.
Okay, right.
Yeah, otherwise, but here I have sort of made a very nice choice where my alcove includes walls that are reflections with respect to the finite simple roots.
Because you want the origin in the closure. So that's why.
Yeah.
Thanks. That was.
But I could choose an alcove away from the origin. Say an origin has already been fixed and I choose an alcove away from the origin, then the walls will be something else, right? They will, yeah.
And translations would be involved.
Yeah, translations of these things, yeah. Okay, so anyway, so now that we have chosen an alcove, A belongs to RA is positive if A of X is greater than 0 for all X in CA, and A in RA is negative if A of X is less than 0 for all X in CA, and okay, and let alpha naught in R plus be the highest root of the finite root system R. Then the claim is that A naught is 1 minus alpha naught check. Oh, sorry, 1 minus alpha naught, sorry. Sorry. Okay. Okay, sorry, I shouldn't have said. Yeah, let me stick to the notation I started with. Okay. A naught is minus alpha naught plus C, where, yeah, C is this constant function equal to 1. Okay, so to see this, I will not fully prove it. I think it is not difficult to prove this, but so note whatever this okay, maybe you can, I think you can immediately see that the gradient of A naught is a negative root. I think that will be easy to see, and you may write A naught as, say, alpha plus, say, n times C, where alpha, I think you can see that this is an R minus, and from this, if alpha plus NC is going to yeah, so from this you can, it is easy to see that n is 1, because anyway alpha plus C will be included, right? So if you are going to go further away, you might as well just stick to 1. So stick to n equals 1. So a simplex, so let me just maybe say this a little more precisely, whatever the simplex is, which includes all the finite simple roots and alpha plus NC, will already include alpha plus C as one of its bounding hyperplanes. So from there you can see that n is 1, and then we know that yeah, so we know that alpha is some ki alpha I, and one of the properties of the highest root, you can see this in Bourbaki, sorry, you can check this in Bourbaki, is that where yeah, I should first write down what my highest root look like. So you can always write your alpha naught as some mi alpha I, where these are some uniquely determined integers. In fact, if you look at the pictures in McDonald's book on affine root systems, these MIs are listed on top of the finite simple roots. Okay, and where Ki is greater than or equal to minus Mi for all. This is one of the properties of the highest root.
Sorry, so throughout you are taking now crystallographic, so like integer coefficient Weyl groups, right?
Yeah. So I'm only working with finite Weyl groups, basically.
Weyl groups.
Yeah, finite Weyl groups. I'm not even, yeah, I'm only looking at finite Weyl groups. Okay, so where alpha is some ki, Weyl groups attached to these root systems that I started with. Yeah.
I
Anyway,
think you started by saying it's a finite irreducible reduced root system. I wasn't sure if that allowed for like dihedral stuff.
No,
You said root lattice, so my apologies. Yeah, that immediately rules those things.
Okay. 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 Anyway, so yeah, you can see that this is one of the properties of the highest root, and from this you can see that again you can see that if a simplex defined by these alpha i's and alpha plus c will already include the simplex that is defined by alpha i's and this minus alpha naught plus c. So using this, it is one can show that a simplex defined by these alpha i's and alpha plus c includes the simplex defined by the alpha i's and alpha naught plus minus alpha naught plus c. Okay, so from here you know exactly what the walls of your alcove are going to look like after we made a choice of a Weyl chamber. They are the finite simple roots and 1 minus the highest root. That's what we have seen so far. Venkatesh, what is the deal? Should I stop now or? I haven't gotten to what I wanted to do, but
like how much time you need?
If I want to discuss this example of AN also today, then I'll need at least another 15 minutes. But I can stop whenever you want me to stop and take it up in the next lecture. Just let me know when to stop.
Okay, we can take it to the next lecture. So, some of the things,
shall I stop right now or?
Yeah, that is fine.
Okay, so I will take it up from here next time. I have basically explained what an alcove is, and I have also we have determined what the walls of this alcove look like. So from here, I will define what the affine and extended affine Weyl groups are next time.
Okay, thanks, Sadhika.
Yeah.
Any more questions? Okay, if there are no questions, let's thank Radhika. We'll stop here and then we will resume again on Wednesday. So Wednesday, I guess, Amit also will. Okay, we'll stop.